Thank you. Good afternoon, ladies and gentlemen. Thank you for being here today. My name is TP. I come from iSTART. My company is located in Hsinchu, Taiwan. This topic, I will introduce cost-effective BIST and BISR solution. Sorry, how to control. Okay, thank you. Okay, this topic covers these 6 items. Okay, the first, let me introduce our company. Maybe few all of you know our company, iSTART. So let me introduce my company first. iSTART, founded in 2010. We focus on memory BIST testing and repair solution. Till now, we provide 34 test patents in US, Taiwan, and China. Our mission is provide the cost-effective memory testing and repair solution to our customer. In current application, I think we want to let our customer get their product list in time. So we provide the efficient supporting system for our customers. And now our eFlash BIST and BISR is passed ISO 26262 authentication. Current application like AI, edge computing, multimedia, these products maybe will use advanced technology. So we make our tool can meet this requirement. Okay, this slide show you our major product line. In our start, this product line, this is the tool-based for SRAM testing and repairing. And heart is IP-based SRAM testing and repair. For some customers, they need to customize SRAM testing and repairing this IP. The final product is the non-volatile testing and repair IP. So using this tool, we believe our customer can improve their product, SoC product yield rate. Okay, let me show you our working flow. In this slide, you can see we have 2 major working flow. They are BFF flow and BIF flow. BFF flow means the BIST future list. In this flow, our tool can do auto identification and auto classification for the memory. And we also can do the clock tracing and auto memory grouping. After these 4 steps, then we will insert our BIST circuit into the SoC chip, SoC design, and we also generate the tester bench for our customer for verifying their system design. Okay, another flow is BI flow. BI means BIST integration information. In this flow, we will integrate all controller with the system top. So we only provide a single path out of your SoC chip. Okay, this is our BI flow. Okay, in BI flow, we also generate the test bench for our customer, verifying their BIST testing. Okay, is in addition to the this is our architecture. Our BIST and BISR architecture, we can see the C means the controller. The controller is in charge of the function selection and test pattern and TIA control. Okay. Sequencer is responsible for the hardware sharing of the test pattern and ordering and sequencing addressing at the same time. Okay. And T means the test pattern generator. Test pattern generator will it's in charge of the executing at the speed instruction and to do the comparison. And after comparison, it's any result. This test pattern generator will return the message to sequencer, and sequencer will return to the controller. Okay, TIA test redundancy analyzer is in charge of controlling the spare redundancy memory. Based on this design, from this statistic, we can see if the memory instance exceeds 4 instances, we can see the area, the rate of the BIST area will rapidly down to 7.5%. If the memories exceed 20%, then the proportion will down to around 2%. Okay. In addition to this sharing architecture, we also provide some very useful design system. For example, we have a programmable algorithm. In this programmable algorithm, we can let our customer design their own testing algorithm. For some memory, this memory cannot, they have some memory fault cannot be detected by standard testing algorithm. So for this special memory, customer can use our programmable algorithm to invest their own memory algorithm. Okay. From this example, you can see to implement this programmable algorithm, just only need to use the very simple supporting element. So based on this example, you can easily to develop your own memory testing algorithm. Okay, next I will introduce 2 special features of our SoC architecture. The first one is the low power design technology. In this, for the low power design technology, we have a specific, we can arrange the controller of BIST in dedicated level of SoC. So the designer can assign the controller to the level you want to specify. And next is the bottom-up flow. In complicated SoC architecture, many IP will be used in SoC. So use our bottom-up flow. You can insert your BIST and repair block by block and block. So you also can automatically integrate all blocks in with the system tab to accomplish whole SoC BIST insertion. Okay, here is I show you the hierarchy specific architecture. For example, maybe in our design we have this controller like INTG and BIST. BIST means BIST repair controller, and RP controller and BIST controller. So if you want to specify this controller to spatial hierarchy, maybe you want to assign this controller to off-domain hierarchy. If you assign this the controller to off-domain hierarchy, if you turn off the power, then you don't worry the power leakage problem. So to implement our BF hierarchy-specific architecture, only 4 parameters need to be assigned. In BFL5, there are 2 parameters need to be set. They are type module name and type hierarchy. In BI, also 2 parameters need to be set. They are type module name and type hierarchy. So from this example, from this picture, we have this system to accomplish this design. So in BFL file, we can set type module name to A, and we also can set type hierarchy to A and B module. In BI, we do the integration. Then we can set the type module name to A and set type hierarchy to A and module B and module C. So after finishing this setting, then you can generate the SoC system like this one, this one picture. Okay, this is another example. This is more complex than previous one. So in this example, we will each separate 3 modules, B1, B2, and B3. So we can set these 3 modules respectively. So in B1 BFL4, we set type module name and type hierarchy to B1 module, and in B2 BFL4, we set the B2 to type module name and to type hierarchy. B3 also do the same thing. In type A, and then we will integrate these 3 modules with type system type A. So we assign A to type A module name, this parameter, and we also assign the A and B module to this hierarchy, to the type hierarchy, this parameter. So we finish this setting, then we will generate the system like this picture, like this picture. Okay. And this is another very useful deny flow. We call the bottom-up flow. So based on this flow, the denier can easily to build a large integrated circuit with BIST. So based on this bottom-up deny engineer also can quickly and get high quality verification at the block. So only 4 parameters need to be specified in the bottom-up deny. They are the BIST interface. The BIST interface main, we can set the JTAG interface. And integrator mode. Integrator mode, we can assign yes or no. If yes, we will generate the JTAG pin out of the SoC. in block pace, we can space some block info file to this pace. If necessary, maybe we need to specify post fixed info this parameter. So if we have a system like this one picture, this picture, so how to implement this? Okay, in deny 2 and deny 4, we can set the BIST interface. Here we set BIST interface is IEEE 5000. And integrate mode, so far we set the integrate mode is no. After this setting, then our tool will generate the block info on this file. Okay, this file will be used. These two files will be used in deny 1. So in deny 1, we also set the BIST interface to IEEE 1500 and set the integrate mode to no, and specify the block info or these two files to block pace. So this setting will be executed in deny 1. So next, we also need to specify the deny 2 and deny 4 .f file to deny 1. So we just need to follow this setting. So we can then deny 1 will know it has true .file in deny 2 and deny 4. So next step maybe is a final step. So we will insert BIST into top module. So the parameter setting will like this. So we set the BIST interface, and in this one integrator mode is different with previous setting. This time we will set to yes, and we also need to set block pace to deny 1 block info this file. If we specify this block info file, then the system top will combine the deny 1, the deny in the deny 1. Okay, the final is the final step, maybe necessary or not. In this setting, we will specify the post fixed info. Okay, then if we have memory, they are in instant. They are being used many times. So maybe we need it will generate the post info of this file. So we need to tell our system we have this file. So follow this setting to specify the post info file to post fixed info, this parameter. After this step, then we will accomplish this deny, like this picture. Okay, let me sum up today's presentation. iSTAR is focused on the cost-effective memory BIST and BISR tool that our customer can easily to insert our BIST and repair circuit into their SoC system. Okay, we provide a very easy setting flow for designer can easily use our tool to insert the BIST and BISR circuit. And our tool can apply to various SoC design. Our programmable algorithm can let our customer deny the proprietary memory testing algorithm. And hierarchy-specific architecture can assign controller to any level of the SoC. the bottom-up flow can apply to the large and complicated SoC architecture. So based on this, based on our tool and these special functions, we believe our customer can use this tool to improve their SoC yield rate. Okay, thank you.